Now this session will probably be quite short because I've already said verbally pretty much most of the content of this session that I've written up on the board. So let me, I can always go to this point. So here, like time is going this way, and you have here a series of like snapshots. Like imagine you had a movie, and each frame in the movie was one move by the Turing machine. So you go from frame to frame, and at each frame you would see the result of one move by the Turing machine. Now this is not consecutive moves, it's just a sampling, but a critical sampling, because you get a feel, hopefully, for what the machine is doing with this task. Okay, so here is our original input stream, here, ending here, starting here. Here's the actual string that you start with. Remember, with the Turing machine, the tape, the infinite tape, consists, all of the squares are blank except for the starting input string, which is a contiguous, no blanks in between, right? It's a non-blank contiguous string consisting of the symbols of your I'm not quite sure which alphabet it is. The details will come. But I guess there'll be 3 symbols in that alphabet: 0, 1, and the hash symbol. Okay? And all the other squares on your infinite tape are blanks. I guess this particular tape, this version, is it's finite on one side. It has an end. And on the other end, well, there is no end. It is infinite in length on the other side of the tape, the left side or the right side. Right? Okay, so we're given an input string. It's 0, 1, 1, 0, 0, 0. That's your W hash, and then the same string again: 0, 1, 1, 0, 0, 0. Okay, that's the string that we input, and the task of the Turing machine, the TM M1. It is to accept or reject that string. Is it a member of the language whose sets are of the form W hash W? Okay, where W is a random binary string, zeros and ones. Now, this history, like the sequence, is it's going from step to step in the computation by the Turing machine. Now, this is not step 1, step 2, step 3. It's not like that. These are just samples. There'll be many steps in between, perhaps. It's just to give you a feel for how it works, for what the strategy is. Okay. Now, in a couple of pages in the text, ahead of where we are now, in fact, on page 147. This processing will be described in much more detail. So, but at the moment, we're just trying to get a feel for what a Turing machine is, what it can do. Okay. Now you know what the task is. We've got to show that this W here, or this substring to the left of the hash, is equal to what's the substring that's to the right of the hash. We have to show this left substring, this right substring are the same. So how do you do that with a Turing machine with its capabilities? It reads. Summarize it a bit. So a Turing machine, it's in a particular at any given moment. It's in a particular state, right? Just like a finite automaton, and it is reading the current symbol on the square where the Turing machine's read-write head is positioned. Okay? So those 2 parameters go into the machine, into the control, if you like, and what comes out are 3 parameters: the next state, the symbol that's to be written on that current square of the tape, and the third thing is the read-write head then moves left or right 1 square relative to where it was. Okay. Right. So with that capability in mind, how would we solve this problem? How could we show that that is equal to that? All right. Well, now the circle here, you could have an arrow, I suppose, a little arrow. I've done it as a circle. Sipser uses an arrow, but I didn't really have enough space for arrows, so I just used circles. But yeah, just a formality. Okay. So the circle means the position of the read-write head. This is your tape. These are snapshots in time. Time's going this way of the state of processing in your Turing machine. Okay, so here's your input tape. The rest are blanks. So this is step 0 in a sense. The very beginning. So you start at the first. At the position of the first symbol on your tape of your W. You're here. Okay. You record what that is. It's a 0 or 1. Okay. And you write over it with an X because you've looked at that one. Overwriting it with an X means you've examined that particular symbol. Okay. But you record that it's a 0. You write an X, and then what do you do then? Well, then you move 1 to the right. So now you're here. Okay, so this step is 1 step after that. Okay, it is 1 step after that. And oh, wait a minute. Yeah. Okay, so you overwrite this one with an X, and you move to here, and then you record that it's a 1, I guess, and you've recorded that was a 0. Yeah, but you don't want to be coming back, and you have a certain amount of common sense and efficiency, I guess. Okay, so you've now recorded that the first one was a 0, and the next one was a 1, and now you move until you get to one place after the hash, as I was saying before, and you look at what's here. Now they're both. Now on your memory, I guess the memory is stored in a state somehow, not on the tape. Now you've got states. Remember, you've got a tape and state, so you can use both as memory. So I guess on your state, you know that this was a 0. And you move to here. Okay, so you're in this position now, and you check what it is, and it's a 0, and you compare with what that was. And if it's a 0, that's fine. You keep going. If this one's not the same as that, go immediately into reject state and stop. Okay, because then this left-hand substring cannot be equal to the right-hand substring. Right? Okay, well, so assume they're the same. Okay, so override it with an X. So that one's been examined and that one's been examined. And now what do you do? Okay, now go all the way back until you come to an X. So you're here. Right? So these two are contiguous. This is the next step of that one. No, of course not, because it's got to move. Sorry. So it's all this moving. Okay. So this comes to the X here, so it's now here. It sees that it's an X. Well, it's done that, so it doesn't override or anything. It just moves back, so it changes direction. Now it's moving to the right again. Okay, it records that that's a 1. I thought it did it up here. Anyway, well, the fine details will depend on the transition rules. There can be a lot of little details. You really have to examine how TM works. But the devil is in the details. You really have to examine carefully the transition rules. What's allowed. Okay, so it reads back, comes to its X, and then moves, changes direction. Now it's here. records that that's a 1 somehow, overwrites it because that one's now been examined, and then moves back to the last x. How would it know? Well, to the next non-x, I guess. Compares that one with this one, finds they're the same, so crosses that out, and it just keeps it just keeps doing this until you have like 2 x's here, and then 3 x's and 4 x's, until eventually you've got all x's and you hit the hash sign. So then you know you've examined all possible symbols in your left substring, this, okay? And then you go to, so then you say here, and then you move one to the right, and you find that it's, if it's a 0 or 1, that's a failure, so you'll go to reject state and stop. But if it's a blank, that's a success, so you go straight to the accept state and stop. Right? Okay. Now you can see, you can just from what I've been saying, there are a lot of details. Okay, so you will, especially when the time comes for you to do homework exercises and problem sessions of the text, you'll get experience with playing with Turing machines. Now we will examine in detail later in the text, well, a few pages away. We will examine the processing of this string by a Turing machine. We will actually examine the guts of M1 in handling this this task.